And unfortunately, I cannot keep the camera enabled. It becomes disabled from time to time, so I don't know why. Okay. Okay, so there is a strong reverb.
Can it be maybe that you have your microphone on?
Oh, because maybe it's too many microphones, right?
Yes.
Thanks a lot for being so polite. Okay, you're right. Maybe, is there any reverb now?
No, no. Oddio.
No, it looks like a little bit is within the normal range, right? So let me just start with, some of you already know what derivatives are, some not, but what I want to point out here is not a theory of derivatives of a one variable function, is to present you the basic notions and methods for basically applied stuff. Okay, so regarding derivatives as measures of change of a function, which most likely will represent a function representing an economic quantity or an economic aggregate, and focus on the measures of change. The measures of local change, starting from a given level of the independent variable and assuming a small shock, okay? Measuring this with the derivative means measuring an absolute rate of change. Using another important quantity in applied economics, which is the logarithmic derivatives, means measuring the relative rate of change, okay? And then there is one more measure, which is called elasticity, which is a ratio between percentage changes of the two variables, the free variable or independent variable and the dependent variable. So this is what I want to do today. Of course, this part is only on the meaning of the derivatives and the geometric interpretation and the economic interpretation. And do not worry here about rules for computing derivatives, because I will present a summary of these rules for two variable functions and one variable functions at the same time, okay? A large, yeah. Sorry. This way? This is what I can, no. This is the most the largest screen I can get. Is there any other trick? Okay. If I no, please suggest.
If you zoom out on the
Oh, I have to zoom out from this, and then I can, this is in again. This is larger. Yeah. Thanks so much. Okay, so basically I was saying, and I focus on both the geometrical interpretation motivation as the slope of the graph of a function and the interpretation in economics, applied sciences, finance, etc., which is basically the rate of change. It's also called the marginal change. The rate of change is also called the marginal change, or the marginal plus name of the variable. Okay, it is a way of denoting derivatives very common in economics. So basically, and very quick, the derivative of a function can be defined as the slope of the graph of a function y equal to f of x at a given point x equal to a. So I will denote this as a, any point, but it is fixed in our problem. It is a fixed point called a. And then we want to measure the slope of the graph of the function at a given point. What is the meaning of slope of the graph? It has a rigorous meaning. It is the slope of a straight line, and remember that for a straight line, slope has a rigorous meaning because slope is just constant along the whole line. It is the tangent to the graph at the point of abscissa A and vertical coordinate f of A, of course. It is a point of the graph of abscissa A. We start from the straight line. We know that the equation of the straight line regarded as a function is slope m times x, free variable, plus q, intercept. And this is already the notation that we used for derivatives, slightly different from the previous notation that we used for the straight line. And the domain of this linear function is the whole x-axis. I pick point A here. This remains fixed in our experiment, okay, also later. I consider an increment h, so I move, for instance, on to the right from a to a plus h. Now this is a positive increment in this case. If the increment is negative, I move to the left. Then I consider the corresponding values of the function f of a here and f of a plus h here. I consider the increment of the function f of a plus h minus f of a. It's the difference between these two coordinates, and I take the ratio of the vertical change over the horizontal change. Okay, so I take the ratio with h. If I put here the expression for the function, which is m times the variable plus q, I obtain m times a plus h plus q minus m a plus q, so minus ma minus q over h. I can simplify everything and I am left with m. Okay, so for the straight line, it's clear that the slope of the graph is m at any point. Remember that now function, take for instance this blue graph. This is a function, it has some expression that we don't care about, an analytical expression of this function. We start from a point A, and this is f of A. We take an increment h, so the increment is the length of this interval, point here, and this is f of A plus h. Okay? We join the 2 points, we have a segment, PQ, and we consider the straight line through this segment. What is the slope of this straight line? Just the difference between the vertical coordinates between the horizontal coordinates. The difference between the 2 points on the x-axis in the denominator is h. In the numerator we have f of a plus h minus f of a. It is the same expression we got before, but of course now it depends on both a and h. Okay? It depends on both. It's not constant like in the case of the straight line. This straight line, called the second line, S, through points P and Q. And it has this slope. Now, what else in this experiment? But H is again an increment. It is positive, but it becomes smaller and smaller, okay? So this means that I'm not going to consider an interval of finite amplitude. I would like to know what is the slope at the point P. Closer